The first book was written from a bunch of lecture notes again that were floating around the web, primarily by Tom Strong. There were 4 authors on it. John Becker, who most of you know is the Unix NIC driver writer for pretty much every driver on Linux. 2 other authors, Savarese and Mike Warren. So this quote, this book has just recently been re-released in 2 varieties. Beowulf cluster computing with Windows and Beowulf cluster computing with Linux. And the reason we have this one here is Microwave's given it away for free. About the first 2/3 or maybe the first 3/4 of the book are identical to Beowulf clustering with Linux. So we brought this one. This is John Loy's actually. This is published at MIT Press. You can go over there and get it. All the Beowulf clustering books that we'll talk about tonight, MIT Press books. This is as of 2002. He talks about message passing interface, parallel virtual machine, quite a few of the major subjects that you talk about when you're parallelizing code and plus the operating system. So because this was so succinct, this pretty much describes a price performance paradigm that is key to Beowulf clustering. There's many ways to get high performance computing in expensive machinery, proprietary machinery, and there's many ways to put together clusters that will give you moderate performance for short money. So we'll talk about both ends of the spectrum and what's in between. Now, I have about 5 websites. If you have to leave early, the only thing you really have to know is I'm going to publish, I'll get Jerry the presentation, I'll put it on my website. Stream Linux is the website of our user group. Some people, John, members of it, it's a Debian Beowulf users group. We primarily use Debian because of our attachment to the package manager. And you don't have to use Debian for clustering. We'll talk about some of the other distros. But if you want to send us email, Debian Beowulf user group at MIT.edu, and we'll send you the links. Beowulf.org is the central point, the central repository for links to software and what have you. It's kind of old in the tooth now. It used to be John Becker's site at Goddard Space Flight Center. It says this.gsfc.org, or whatever it was, nasa.gov. It's now Beowulf.org. And all the Linux drivers that Becker wrote are now over at skill.com. He's the CTO of Skill Beowulf operating system. So a lot of the things that you will recognize from the says this pages are now either skill.com or Beowulf.org. I don't think Beowulf.org is skilled anymore. Just Linux drivers are skilled. And of course, you can download Skilled. Skilled is a Red Hat variant. I don't think they're on the 2.4 kernel yet, but Skilled affords you is some very nice to have Beowulf tools, and we'll talk about those. And we'll also talk about other resources. Okay. So how do you build a good, fast, and cheap cluster? When we talk about clustering in general, and particularly Beowulf clustering in general, we'll talk about some of the ways to get failover capabilities and load balancing out of just general purpose clusters, not necessarily floating point intensive clusters. You look at the design of your client node. Virtually every Beowulf cluster has one really powerful head node and lots and lots of client nodes. As many client nodes as you can buy, based upon your price performance ratios. So the variant Andel's rule of thumb is if you've got a 1 gigahertz processor, generally speaking, that'll give you about a fifth as many flops or ops. We care about flops. If you care about ifs or ops, then you probably can go to a different CPU. You can go to Transmeta Crusoe, which is great for serving up web pages, not so good for floating point performance. But Beowulf, scientific computing, people love the flops, so we pretty much rate everything on flops. So a gigahertz processor, generalized. We have 200 megaflops. You can do better. It's very application code specific. But for the longest time, we didn't have a network topology that would finish this equation off that was anywhere near the same price-performance ratio as our high-quality CPUs that flip over on Moore's Law life cycles, and our high-quality RAM that moves Moore's Law life cycles. So here's ASCII white. Now, you see the rows and rows. This is a very highly, I'm pretty sure this was this IBM. This was the Strategic Computer Initiative busted up quite a few of these teraflops machines to a couple of different vendors. I think IBM got 2 of them. I got probably ASCII white and ASCII blue. There's 2 ASCII blues. And the vast majority of these are client nodes. They've got a head node that puts all the distributed processes back together, but so otherwise it's a traditional head node client farm Beowulf. But this is the very high end of the spectrum. It'll give you all the ASCIIs get between 1 and I think 12 teraflops, and they're all Department of Energy grants. They're fantastically expensive, very customized. This isn't a commodity off-the-shelf solution yet. It is. And so now, see, we're not even the ASCIIs used to own the top of the top 500 list. And then along came the Earth simulator, which is 43 teraflops. The Japanese just completely shattered the world speed record. So now there's a couple more clusters, the 2008 cluster, Los Alamos, and we'll be up into the double-digit teraflops. So, all right, on the other end of the spectrum, Stone Supercomputer is a cluster that they put together out of donated equipment at Oak Ridge. Once again, a Department of Energy facility, and an early Beowulf cluster. So their price-performance ratio is 0. They've got nothing into this. They don't use 486s. It turns out that on the optimization scale, you're not going to be able to get data in and out of a 486 in any reasonable amount of time to make it worth your time and effort. We'll talk about some of the total cost of ownership concerns on running machines that don't give you enough performance for the amount of labor and cost of even running. There's a lot of 1,000-node clusters out there now. There's not that many 2,000-node clusters. Some of the algorithms for putting clusters together in subgroups and constellations tend to break down after 1,000. Everything, a lot of the network topology decisions drive that. Little pockets, little pods of 64 nodes. That's a pretty well understood business right now. You can get information on how to set those up off a Keville website. And then fast. When I use the term fast, I mean how quickly can you field a cluster? If you've got a pending problem, if you want to find what the 1 billionth digit of pi is, and you need to put a cluster together really quick, there's a couple of ways to do it. You can call up microwave, and that's all they do is sell clusters. Most of them are scientific application clusters. They sell to university and government agencies. The big guys don't do traditional ATX case Beowulf clustering, but they do bladed solutions. Everyone is into blades now. We'll talk about some of those solutions. IBM is into Linux clustering in a big way, but it's not commodity off-the-shelf clustering. It's typical IBM approach, rock-solid case designs. So because of the phenomenal success of the middle range of clustering, everyone, Sun has blades, everyone is getting into some facet of multi-path solutions. All right, how does it work? Why is it a Corona model? The cluster phenomena apply to almost everything, or quite a few things that any particular IT department is doing. Certainly, web servers are perfect for it. We'll talk about one of the blade companies, LUG Technologies, sells a 4U rack that you can just throw as many blades in. I think it's 16 or 24. We have and use round-robin DNS. You throw these blades in. They you can either distribute a website transparently across them. They've got 3 NICs on each card. You can channel bond them. You can do a alternate. I mean, if you lose one, you can come into it via a serial port. It's got more redundancy than you'll ever need. But it's targeted at people who are bringing a web server or possibly, well, some tech-based server over to a co-location facility, because it's based upon the Crusoe, so it doesn't draw much in the way of power. It's got very good. It's just got a heat sink, not a fan.
Which 4U rack did you show us last time we were able to feed down in the mechanical lab? You said it was really low cost.
Yeah, that might have been the LUG Technology. The 2 guys at Beowulf. Or
Is that it?
awesome. Yeah, I think it was the LUG. We have the picture. They've done quite a few things that people who work in data centers requested. They said, I want to be able to turn on a flashing red light when I have a hard system threat, or I want to be able to do hard reboots just by pinging. Or it's quite a nice design. They've got an interface, a web-based interface where you can log in and do explicit load balancing if you're on the client. Okay, we used to build supercomputers and high-performance machinery with Gene Amdahl's law, as a. This is a bit of a generalization, but if you've got something that parallelizes embarrassingly, like calculating pi, I think it's a series of kilocut long. Well, you have to put all that together at the head node. So you've got this serial recollection at the very top. You've got 1,000 nodes calculating pi, and you have to reassemble. So the fastest you'll be able to go is the amount of time that serial phase takes you. And this used to pan out quite well for years when they were designing machines. But 2 years ago, Russell Kant did a study of all the machines on the top 500, and it turns out that all of them were outperforming what Amdahl's law would have predicted, all of Beowulf. So I have this analysis. The cluster conference from 2 years ago in Los Angeles. They have these proceedings if you want to look at them. Most of these are available on the Cluster 2001 website. And then last month we went to the Cluster 2002. And you can look at this too if you want. If you want to look through the table of contents, I have no problem loaning this to anybody. It's just that most of these presentations are not on their website. This one has anything you find here that you might want to read about parallel virtual file systems, you can get online. This one doesn't look like they're going to put them online. Only the presentations are online, not the full papers. So this was Kant's description of what's going to limit us. We have, I've got another slide that talks about what kind of limitations they have. So Beowulf clusters, as a subgroup of clusters overall, benefit from the phenomena that you have when you maximize Metcalfe's law and you cross-connect everything you have. If you've got 2 CPUs in SMP versus, if you have 4 CPUs in SMP versus 2 CPUs in SMP, your average number of idle cycles per CPU is less. This scales. This scales pretty well. You're going to run out of money before you start having arithmetic drop off or scaling SMP or rapid IO and some of these CPU cross-connect solutions. Some of this is by virtue of the fact that you've got distributed cache, you've got cache coherence, cache copying, these units, you've got shared memory. So there's all these nondescript benefits to having multiples of smaller rather than singles and short numbers and big. And this is how, this is assuming we're getting a third of the flocks out of a 500 megahertz machine that we are out of a good 1500 megahertz machine. That's your UltraSpark. That's your monolithic, nice UltraSpark 2 over there. That is going to be obsolete before you statistically can have a failure. The Sun guarantees 5 nines on the top of the product. Whereas the El Chico machines, you're going to have 1 out of 1,000 die. So whatever, you're going to have 1 die in 1,000. You're going to have 1 out of your 1,000 nodes die. But because you're building to take, because you expect failures, you can build to take advantage of it. What this allows you to do is you'll have 3 times as many failures in this particular solution than you will in that one. But at that one, if you have any failures at all, it's a single point of failure disaster. So your mission critical application will go down in the middle of the night, and the only thing you can really do to keep that from happening is have a sysadmin on a beeper. Well, this one, you don't need a sysadmin on a beeper, because if you lose 1/3 of your functionality, you just go in the morning and you swap it out. You swap out the motherboard. So it turns out that this entire enterprise is substantially cheaper than that price. And like I said, you're going to have failures over here, but you might as well embrace the failures than have to worry about having a negative. That was one of the big selling points in the early days of clustering, was the single point of failure, the Andrew Carnegie solution wouldn't destroy your enterprise. It's a tougher pitch now because Sun is clustering, so it's even better if you can cluster, really long lead time between failures. Avalon was this was something of a high watermark because this was Tom Sterling's machine. It used channel blending. He did a side-by-side comparison with a vector machine of some variety, and price beat it on every standard you compare with. Price, certainly, performance equal or better. Of course, all the, like I said, the implicit benefits of clustering. Loki, we talked about Loki. This was one of John Becker's. This Clap 2 and a similarly designed machine in Australia called Plugin. This came out about the same time that people were porting their floating point code over to the x86 graphics extensions. And you get a better bang for the buck if you can move your floating point code into SSE in half as many cycles as the same floating point. So this is the University of Kentucky. He wrote quite a few papers on this. The other thing he did was back when big wire speed fast Ethernet switches were expensive, he wrote an algorithm to break up your network traffic into multiple smaller switch solutions. We call it a flat network neighborhood. Bunyip called it something else. And what it did was, because the price difference between an 8-port fast Ethernet switch and a 16-port fast Ethernet switch was more than double, this thing was quite an inexpensive solution. And as it turns out, he was getting pretty close to 300 megabits out of 3 network cards. You certainly get 300 megabits out of 3 cards channel blended. A lot of people are still channel blended because the price of fast Ethernet is so cheap now. Okay, well, what can you do with, well, we already said what you can do with clusters in general. If you buy 2 cheap machines at a quarter of the price of the equivalent one good machine, then you have some built-in redundancy. Even if you do have a failure, you may, at least you have uptime. It may be reduced performance, but at least you don't have single point failure. That was the big selling point for the longest time. Now, the selling point is, you can still, there's the Moore's law is forcing the performance and the node size and the die size and everything into into much denser packages so that you can hit the next level of clustering. You can start clustering groups of 8, groups of 64 until you hit another enterprise problem like 100 by 64 port gigabit switch. That'll probably be the next level that you have to say, well, maybe I'll just take longer to calculate my problem. But these are the traditional, the Gordon Bell Prize. I've got a couple slides following up on that. Every year at supercomputing, they give the Gordon Bell Prize to the person who has a supercomputer that can calculate flops for the cheapest. It's the price performance unit. And setting it home, if you log onto their page, they claim to have hit the Zeta flop about a year ago. So by many definitions, this is they send you a chunk of data, they run a couple fast Fourier transforms on it, and they send it back. That's certainly one application. Most of the scientific computers that I've seen in practice are running equations. They may not even have temporary data, and a lot of them don't even have a hard drive. They're diskless nodes. They're just calculating a portion of multivariate differences. So the city-at-home distributed solution can have fantastic latency. City-at-home sends a chunk of data out to 2 double-blind recipients. If you somehow figure out a way to hack in artificial intelligence into that FLT and it comes back, then you can compare it to the other blind one. So they can't spoof city-at-home. They've been through their data. They've basically restarted on their data set because the screensaver was so popular that now they're looking at it in a finer grain. No. All right, so Loki was Becker's machine that he built for $63,000 in 1960. The gigaflop machine, the Beowulf cluster. And to rebuild that machine in 97, it would have cost you less than $30K. And to rebuild it in 98, it would have cost you $15K. So he entered it into the Gordon Bell competition at Supercomputing 97 and won with the figure of $50 per megaflop. Now, I don't have the 99 entry here on the next slide, but this is dropping off much faster than Moore's law would. Moore's law, so Moore's law is actually an observation. Gordon Moore said in 1965 that for any given die size, we'll be able to put twice as many transistors in it every 18 months. And they've managed to stay either on that schedule or ahead of it, due in part to some technological changes for a long time, much longer than Moore. So Supercomputing 2002 is coming up next month, and we don't know what's entered. Just so they keep this competition somewhat secret until it comes out. But 15 cents a dime per megaflop. Now, when the price drops to that level, every little lab can start doing whatever particular computational fluid dynamic problem it has.
Can you comment on the hardware being used and actually the sort of size of the cluster we're talking about? Because price performance doesn't tell you absolute performance. You suggested that, well, any lab can do fluid dynamics, but not if it has the total capacity of an iPad.
That's right.
But it only costs a nickel.
Right.
So what are you actually looking at?
Well, I can tell you on some of these machines, Batu is a 66 motor of Athlon. Actually, they were the slot A Athlons.
Okay.
Less than 1 gigahertz, 600 megahertz. Three NICs each, 9 switches. Some fairly sophisticated application code to take advantage of the 3D now. But otherwise, it was something of a turnkey system. It was a simple OS install, Red Hat, I believe 6.2, And it's taken the weekend to put together a simple ATX box, ECC land.
I have an application that's not ray tracing or doesn't do heat distribution on a chassis. It's not, by its very nature, intended to be a parallel process. It's a serial process. We talked about parallelizing a C program. Are there lots of what do people do if they have a problem that isn't the kind of problem that you normally think of, that you're going to put parallel supercomputers, parallel boxes, those machines run applications which are by their very nature parallel. When somebody does a universe simulation, from Big Bang forward, that's done on lots of different processes. It's by its nature parallel. I have an application which isn't. What do people do who have real-world applications with? Go ahead.
Well, there's a class middleware that is resource management. The Mozix, you tell Mozix what you've got for resources, and it will determine how to distribute your problem up over the set of resources that you have. Some other packages like Infusion and like Infusion will run a copy of your app with different start and stop parameters on. So if you've got a 10-noder, they won't intercommunicate interdependent variables, but it will run, say, your sim from 10 to 20, and the other one will run your sim from 20 to 30. It doesn't quite qualify as a parallel processing, but there's these packages are a response to people with very serial apps.
Yeah. Okay. Thank you.
So here's the RLX box, and these blades have dual notebook drives. We've got some other printers in there. I think there's room for 2 sims on it. Backplane that, like I say, you can access with these big RJ 12s, I guess, where you can speak to subgroups rather than multicast. You can speak to every odd blade or even blade. And this is partially so that if you have a hard failure, you can code around it. Yeah, they're still using Crusoe. They're using the next-gen Crusoe TM50. And this is called Omni cluster. It's got a P3 in it, and you can stack a bunch of them in PCI slots. It's got PCI to PCI boot time. It's got a NIC that you can access in video, and there's a lot of SPC solutions that are coming out that answer that need for people who not only have a lot of PC but a fast PCI system.
That's a complete computer.
Yeah.
How much are those?
The ones I was looking at were a grand. What level of P3 it had? It was $1,000. So.
Well, do they make them with AMD chips?
Not yet. No. Part of the reason is you're not going to be able to stack these if there's anything that has a heatsink on it, or a heatsink.
Well, those are designed to be put into a PC, right?
Yeah. So you've got less than a U between PCI slots.
Well, you don't put them in regular PCs, you put them in backplane.
Passive backplanes?
Yeah. So,
Oh.
well, maybe you'd have one big long one. So maybe space between PCI slots. And this right here, if the that is 8 motherboards on rails, and they've got either single or dual solos. Now this wouldn't be, so if you had any number crunching to do, it probably wouldn't be a good solution. But if you needed an outboard rendering box for your Abreau or cloud PBM experiments, or cloud API, or cloud modules. Cloud is, if you've never seen this app, it's
Persistent division.
It's rendering is a very similar parallel. You can just keep adding client nodes and just keep getting that arithmetically better performance out of rendering. So upward boxes like that, which there are a couple of manufacturers now. I'll remember the name of that one. I believe it's called Redstone. Redstone.com.
Redstone.
Redstone. Yeah. And they've got the name of their app that you can log in and do all your remote admin to motherboards that don't have video cards on them. It's called Houston, and that's a free Linux package. And then I'll pull up their website. They've got a couple other things that they do on their website.
What's the difference between blade computers and the single board computers?
This one, you have to come up with your own solution to deal with multiple SPCs on PCI. This one, like that one, has it's called the tower control. There's a single layer of abstraction to talk to with layers. You can talk to a, well, it's still, I can tell you that a skilled Beowulf operating system does this function too. There's a single IP address, there's a cluster IP address. So any action you perform on that IP address gets distributed to all the IP addresses. You can ping it, this thing will come back and it'll tell you if there's any dead cluster nodes. The interface for the RLX machine do the same thing. You have a single layer of abstraction, a single system.
That HPC solution you're showing right there, that reminds me a lot of something that you showed in your lab before. It was something you were getting to price watch. And I'm not sure if that ever worked out for you. That's what my question is. Did that work out for you? You were able to put a dual motherboard, a dual proc motherboard in the front, a single proc motherboard in the back, and some hard drives in each pullout. And then you were able to stack these. I'm not sure how many you said per room.
Oh yeah. Okay. Well, so one of my particular research interests is just this cluster. It looks like this lab that we have our Beowulf, our Beowulf cluster app is going to take over the diskless Debian package management, and it needs a little bit of work right now. There's diskless packages in Red Hat is actually quite mature. There's a lot of labs out there that are running all of their client nodes diskless. You turn them on, they either, the way Skilled does it, and by the way, Skilled was like one of the last words left that people haven't co-opted from the original Beowulf method. It's on the Angular reference, Skilled.com. The way you add a node to a Skilled cluster is you turn it on and you throw one of these floppies in it that you made off your head node called Beowulf. And it just sits there in ARPS. And your head node whacks the MAC address, sticks it on the DHCP server. Next time the thing reboots, it'll pixie boot, it'll get ether boot, it'll boot disklessly across the network. Now, most of your motherboards are coming with this in the LAN now. Excuse me, the BIOS. Boot from LAN. A lot of motherboards have an EE Pro right on them. It's easy to put a machine like that into a cluster. And they don't all have those set as a default set. But you can take, you can get a Linux boot disk and put the NVRAM settings in, and you boot from that, and it'll tell you to boot from that first. There's quite a few of the diskless clusters you can do completely blind now. You put your NVRAM flash in, and then you put your DO boot thing in, or the other way around. DO boot will ARP, and I guess Kickstart will ARP too, right? Is that
Kickstart will ARP as well, and you can it'll DHCP for its hostname and IP and so on.
Okay.
I haven't done it in a long time, but I think it does that.
Do you need to run a separate DHCP server? Can you just run DHCPD as part of like the head node or something like that?
All the clusters I've seen, because they want everything to come out in the numerical order, they run one of the ISC 3.0 DHCP servers, so that so that you know what node gets what IP address, and then so that it's not free for all. That way you can just look at the flash node lights, because like I say, these distance clusters don't have anything in them. Well, they've got floppies, but they don't have video cards. These are ridiculously cheap client nodes from lots of them.
Just wondering how that would apply to, like, let's say, the Linux terminal server project where you can statically assign IP. Now, would you still be able to statically assign one IP for that one cluster? Or would you have to have, let's say, just an internal DHCP server where you can statically assign numbers out as go based on MAC address?
Well, in fact, if you go to ltsp.org, they have a little script there. So what he's talking about is Linux Terminal Server Project, which is, they're at the forefront of the distance clusters houses. There's a script that after the thing arcs and after you grab the MAC address, it will append a record to the bottom of the DHCP.com. Now, generally speaking, everyone's using private IP addresses, 10.0, and they're using RSH. Security is absolutely a non-issue on a private cluster. In fact, so most distance clusters get their kernel from TFTP, which is within security itself. So if you're working from that level of understanding, and that your cluster, your wildly insecure cluster is behind a firewall or a locked door, then this is a pretty good solution. And I think you can get the scripts for building your internal all your client nodes and then build your .conf file.
And that's all at ltsp.org?
Yeah, these are the ones that have the, it's got a strange name. The actual name of the how-to, I think, is Pixie. Boot.html or something. Yeah, it's an awkward URL. But my first distance cluster, I followed this recipe to the letter and it worked right out of the box. It's a very well written how-to. We can pull it up after. Okay. Moore's law is really making clustering happen. I used to have a sample here, the one I can sample, it's not working, so. The only things I wanted to talk about that aren't Moore's law related are the Blue Gene project with IBM. They're not big believers in balanced clustering. They unbalance it based upon their particular needs. The Blue Gene project is now that we understand the 40% improvement per year. Well, something standard, die size, price, whatever, and you're going to have a 40% performance. Well, you'll notice since they released the Pentium 2, this curve has actually gotten to more like 60%. Well, up here, by 2001 is the Titanium. Over 300 million gates and 130 watts. Nobody's clustering Titaniums yet. So, because clustering takes advantage of Moore's law phenomena in CPUs, RAM, hard drive performance, the whole 9 yards, clustering is like Moore's law on steroids. Especially in recent, this scale is 94, and you have to crush it down by a factor of 10, and you have to crush it down by another factor of 10 to show what's going on since the start of the Strategic Computer Initiative. So, like I say, all the ASCIIs are in this single teraflops. These graphs, by the way, are from Jack Dorngara, who's one of the writers of the MPIC book, among other things. Runs the top500.org. He also has a subset called topclusters.org. So if you want to see where your cluster weights amongst others, in many categories, very subdivided by database issues. So these are the single digits of teraflops. And up here is the decimator, that means 43 teraflops. And so the next year or so, we're going to see probably yet another exponential jump in performance of the big guys. Now, there's the big guys, and then there's everybody else. The top 10, Jim Gardner's done lots of stats on this, the top 10 machines make over 50% of the processing power of the top 500. Okay, so here, this slide's kind of long, but wanted to demonstrate how every Moore's law generation on the subcomponents that you use in building a plan, they've all been moving pretty much in lockstep, except for one, which is network speeds, modem speeds. Turns out the alpha, lots of people cluster alphas. This goes way back, and the Alpha Linux project is quite mature on their clustering packages. The alpha is alive and well. So to calculate, if you wanted to go in and put your machine at Exodus, they would give you a 20 amp circuit and they'd say, hey, you get this whole stack, this whole 66U 19-inch rack, but you'll never fill that up with titaniums and be able to run on a 20 amp circuit. So Blade people saw this as a market where they could sell you low power devices and you'd be able to run your enterprise server at Exodus and fill up the whole rack with 20 amps. Well, that doesn't apply to academia, which is where most of the data is. It doesn't apply to Department of Energy facilities and government agencies either, because electricity is in the overhead, and the amount of electricity you use even on 64, like I say, if you've got 64 nodes that are running, let's say conservatively 250 watts per each. Although all the Athlon machines say you need a 300 watt power supply, then you're generating 33,000 BTUs per hour. So you need a specialized piece of AC for that, or lots of fans and all that over windows. It runs the heat. The cost of removing the heat rapidly becomes a priority rather than an afterthought. Power usage rapidly becomes a priority, but not in many of the traditional super or scientific clusters. Okay, so we use Debian. I haven't tried Midori Linux yet. I would assume Midori Linux the RLX boxes ship with either Red Hat or Windows 2000, I think. They don't ship with Midori Linux. But they did experiment once with Debian 2, so the different potato. Generally speaking, if you've only got 48 nodes, you're working at a command prompt. All of our scripts are basically just single line RSHs that we multiplied for the number of nodes we have. Now, that's a somewhat Byzantine way of doing it, I guess. If you're using skilled, you don't have to do that. You can call a command on a single IP address, and you'll still get the same amount of data back. If one of them doesn't ping back, you'll know which one. It'll tell you what. But most, I have to say, most of your sysadmins that do, 48, 64 node clusters do everything at the command line. They usually do the scripts. The other good thing about skill, they have replacements for everything. They have BPSH, which is a replacement for SSH and RSH. This has slightly less overhead, so we do a lot of shell scripting. This won't be as much of a performance as this. There's been a fairly large thread going on the Debian Beowulf list, Debian-Beowulf, about the overhead associated with running things in RSH. This is also, Debian also has something called DSH, distributed shell. I haven't tried this one yet. vproc is another thing from Skill's Beowulf operating system. If you start noticing performance problems, there's probably someone who can investigate this and grab utility. So, going back to Sterling's description of Beowulf clustering, MPI, in particular the public domain ones like MPIC and Land MPI, they are very mature message passing libraries. MPIC, here again, you can go get the MPI books over at MIT Press. Has quite a bit of skeleton code. If you have a rough idea of what you want to do, or you have an app that you want to figure out how to move portions into, it can tell you how to parse your code and get a rough idea of what can go and what can't. Some things are, by definition, serial, but generally there is some parallelized portion of your data. So I'll get a little bit more into detail on that. Parallel virtual machine, there's a new rev of this coming out pretty soon. LUG, I'm one of the DOE consultants who wrote this book, and there'll be a new version of that coming up. I don't know too much about parallel virtual machine. MPI seems to have the vast majority of the market share. There's a couple of commercial versions that need to be able to buy them, but given that C1 cards, MPI Pro, Misty.
Does PBM work under Beowulf?
Yeah, you can get, if you take your package manager of choice, RPM, you can find it, it'll come right up. You do RPM pick, it'll install it. Everybody's hit it to this now. So your client node isn't running anything but what you want. It's not running syslog, it's not running sendmail. All it's running probably is the multi-purpose daemon. And especially this disk list, you don't want any interrupts jumping in. You'd be surprised what will give you performance hits. Once you've got your client node to where you want it, then you can clone it, especially with some of these operating system packages. Once you've got some of them, VA Linux had a package called system node, and you would define a client node as your golden master. And every node that you threw in, it would get cloned off the golden master. There's quite a few solutions like that. Once you're comfortable with how your favorite client node is working, everybody gets that kernel. Now, MPI uses something called machines.linux, which looks a lot like your host file. Machines.linux file, it's all in cache. You set this up, you tell MPI what machines you have, node 2.mit.edu, tell it how many processors you've got. And you can send it a command to invoke your app is, your internal app is MPI run. MPI-run processors, so you want to use 70 of your 80 potential processors. It'll look at your machines.linux list and it'll grab the first 70 processors. And then your app. So CPI is their demo app. You get the sources for calculating pi. You GCC it, and when you run MPI run-n 70 CPI, it'll not only tell you what pi is based upon whatever the preference, whatever your grain is, but it'll tell you the block clock time it took to calculate it based upon how many processors you have. So CPI and FPI for you get all the fortune sources, you get all the C sources when you install them. It's MPIC now, MPIC 2.0 is going to be one of the most simple installs. You can download it as a tarball or as RPM or dead. That's MPIC. Yeah, it's the MPIC is MPI, and CH stands for the CH device, which is something they invented at Abreau National Labs, which is ANL.gov. This is the home of MPIC. In fact, MCS.ANL.gov. And it turns out they were the hosts of this conference in Chicago. They're running quite a few of the interesting projects out there. I'm involved in one called Don't Laugh, the PlayStation 2 Beowulf project. The reason it's a serious project is because it turns out PlayStation 2 not only is shipping Linux for $100, They've got the 2.2.0 kernel. You can get it for $100 on a hard drive, so it's worth it. But PlayStation 2 is based on a 128-bit MIPS chip. That's what the emotion engine is. So someday, this is going to be one hell of a graphics processor. It isn't now, but there's a lot of Linux developers that are looking at this for the future.
I'm just gonna ask this question. You already covered this, and maybe I'm wasting everybody's time. Let me say my question first, before you turn around.
Okay.
The idea of putting multiple small computer boards in a PC is the cheapest implementation of that you know about $1,000, or can you buy? Years ago, I'm talking 20 years ago, I thought about putting Z80s on boards and putting them on an S100 architecture, making a parallel computer. I was writing compilers in those days, and a parallel computer would have been worth something. But actually, the problems are really hard to put a Z80 on an S100 board. Are there cheap machines today that somebody can put into a PC? You showed me 3 machines, $1,000 a piece in a PC.
Yeah.
I'm not talking about that. I mean, you know, fairly inexpensive machine, say with only a 1/4 meg of RAM, no video card, you know, just basically a raw computing type machine. Plug into something else like say a PCI board. Does anybody make something like that?
The short answer is no. There's been a lot of people who are looking for a motherboard that's strictly for clusters, that doesn't have all that other jazz on it. Now, it turns out, I'm very interested in clustering micro ATX boards because they fit a couple of form factors pretty well for micro-inch chassis. But most micro ATX motherboards have sound on them. They've got, heaven forbid, a parallel port. You know, stuff that you'll never use on an outboard processing board. The other thing they don't have, none of them support ECC. And you almost have to have ECC there. I can't think of, it's okay to drop a pixel here and there if you're trying to rebuild the holodeck, but it doesn't cut it. If we want to calculate pi and the digit you lose is way up in the top 5, people are going to notice.
I thought at one time, maybe they don't even do this anymore, Microwave had, this is when pieces were 286s or 386s, they had plug-in cards that had like alphas or something on them with memory that you could plug into your PC. They could do that kind of thing that really was just designed as a simple computer, CPU and memory and nothing else, and you had to use their specialized development system.
Yeah.
I don't know how much that cost.
Yeah, they had
probably
fairly
fairly
Screamer or something. They had a bunch of interesting bit blaster things like that.
Yeah, yeah. So that's a possibility. At least it hits the right level of technology, but maybe anything specialized is more expensive, and that's what you're asking for. Yeah. The other possibility is there are the single board computer thing. Basically, the big market for that is embedded systems, industrial systems with passive backplanes, and that stuff tends to be fairly expensive, but it's certainly you can get CPUs for less than $1,000 a piece. That I can guarantee. Yeah. I priced stuff out 2 or 3 years ago, and it was less than that then. The issues you pointed out is if you're plugging in the PCI slots, how densely you can pack them with the heat constraints and the fan constraints.
Yeah. Yeah, there's been a lot of attempts at the CPCI and VMA solutions, but it seems to be mutually exclusive, both performance, floating point performance, and low heat. So, and heat has killed many a good design.
So if you're trying to get in, somewhat fast processors for under $1,000. Used laptops might be easy with that.
Yeah, there's a couple other things.
You can buy used laptops for like $100 these days.
There's some interesting things with that.
Yeah, those don't go, you can't put those on the shelf and expect them to keep working.
Why not?
Some people do that, but maybe I'm unlucky. I own lots of laptops, and when I leave them on for a long time, they tend to die.
But what dies on it?
Different things.
They get hot, right?
Yeah,
Well,
they get hot,
I
they
mean,
die.
If you're turning off the screen and you're not using the keyboard and the mouse,
They still get
They
hot.
get hot and die.
If you're processing, they get hot.
Yeah, they get hot and die. You can't use a laptop like you can an AMD, desktop.
Well, so AMD has a new app called Power On. Is that what it's called? Power On will throttle down your megahertz when you're not doing any number crunching. And it's designed for laptops, but it'll drop your power usage if you're below 60% IOS or 40%. I forget. I think you can set it. It's a pretty interesting thing. The other good thing about laptop motherboards is they use the 44-pin ID. So 44-pin ID takes power off the last 4 pins. So you could theoretically build a cluster that you don't have to hook up any power wires. You don't have to put a 5-pin 5-volt connector to a floppy. We built these things with these little things called Linux disk on modules. And I got some pictures of those. But the Linux disk on module takes the floppy power connector. And we'd love to be able to do that.
Back to heat management. Last time I came to your lab, we were talking about those price watch cases, and we brought up, kind of ties into what you were talking about, we brought up the SwiftTech manifold heating where you pump water or fluid through them, and it seemed that that would be a natural fit with your low-cost price watch, U-racks, pumping in water into SwiftTech manifolds that are stacked, 3 manifolds per level, multiple manifolds, and then coming out through 3/4-inch pipe, and then just putting that into a central heat exchanger like a car radiator.
Yeah.
Okay, but since then, a more elegant solution, but vastly more expensive, is a German case called Beowulf. I'm not sure if anybody's heard of it, but it's basically a cube refrigerator that you plug, your motherboard into.
Really?
I haven't had the pricing until somebody's come out, from what I understand. Haven't done the pricing for it, but it is commercially available. Vapo Chill.
Well,
VAPO Chill.
Shuttle makes these, I don't know if you've seen these, they have them at Maker Center, SS40s and SS50s. Shuttle makes these things, and I think one of the fascinating things that they do is, to get the form factor down, they don't have a fan on the CPU. They have heat pipes feeding into the case fan. So they only have one fan to evacuate all the heat out of the box. And the heat pipes just sit there and reflux. I guess they're slightly evacuated, probably distilled water, and the water runs up and down, moving heat off the CPU. I think it's quite interesting.
It's a thermosiphon. It's just, the hot water brings itself up, and then cool water.
I'm assuming it's depressurized, but it may be methanol. Maybe it's not depressurized, and it's just something that boils at 47. So, yeah. So they took one more mechanical thing. Anytime you can take a mechanical thing out of your client node, I mean, we're talking about a bunch of client nodes. We're going to have failures. So let's get the mechanical stuff out of there. That's why I'm looking at these Linux just on modules that are a piece of flash memory on an IDE card edge. There's a disk on chip. If anybody's ever looked at the Linux BIOS project, they tell you how to put a Linux microkernel into the basically 256K EPROM. And it's only enough to boot something that will get either boot out the DHCP. That's what Linux BIOS is. Well, actually, they're getting better. A lot of motherboards now are shipping with 4 meg BIOS, so because they forgot to implement USB. So you can put a lot of performance. So I was just going to say what's keeping us from this slide's kind of cool. But if anybody's been to the Intel site recently, they've done a PCI NIC, and I think it's PCIX. 10 gigabits is a lot to be getting out of a PCIX motherboard. So Even though the new PCIX chipsets like the Grand Champion from ServerWorks deliver unbelievable bandwidth, 64 gigabits per second on the memory bandwidth. Pardon? Intel's got this, yeah. Now, I don't think they're shipping this yet. I played a lot with the gigabit cards. They have a 32-bit gigabit card for $50. It's the Pro 1000 MT. And what's strange about it is it's a 32-bit 66 megahertz card. So if anybody's ever found a PCI bus that's 32 bits and 66 megahertz, that would be a godsend. You could populate a motherboard with gigabit card in a 32-bit bus. You will hypercube that. Or generally speaking, I think that's just for people who use 64 or 66.
Are technologies like MirrorNet still thriving, or they kind of died off with the advent of some of these other?
Well, most people in the commercial business will tell you that VIA has died in the commercial. VIA has pretty much been co-opted by InfiniBand. VIA is alive and well in the home hacker business. There's the MVIA project. You can download that from who's posting that. There's another open source protocol project called Gamma that's based out of Italy, and they claim to be getting MirrorNet style latencies out of standard E Pro Recon telephone cards. So and latency is the killer for clusters. Everybody wants the 2.5 kernel done so that we can get rid of latency in the kernel. But it's certainly been the problem all along with network cards. MirrorNet has been the performance leader since day one of that. They've always had the lowest latency. They've always had the highest bandwidth. There's a site called conservativecomputer.com that publishes the bandwidth to the PCI bus and then bandwidth out. And the ServerWorks MirrorNet card combination blows doors off everything else right now. But it isn't cheap. You can't get into a single MirrorNet card for less than $1,000. And these are point-to-point devices. If you want to distribute, if you want to build a huge fat tree on your MirrorNet cluster, you have to buy switches, spine cards and line cards from MirrorNet. You can run into some serious clunking. But it's got spectacular latency. It's single-digit microsecond latencies.
Kurt, what have you found for down-to-earth cards, the cheapo cards?
You can get, well, out of TCP/IP, you're not going to get single-digit microsecond. You can get, you can find gigabyte cards on eBay real cheap right now. They've got very low latencies. Out of the Ethernet and gigabit Ethernet, you pretty much have to go with one of these experimental protocols. MVI is supported on the E1000 card right now, but on the 2.2 code. They're not quite there yet on the 2.4. But the latencies on some of these VIA implementations are pretty interesting. You can pull up those sites too. They publish their laboratory.
What's the website?
Pardon?
What's the website?
m-via.org. So there used to be viaarchitecture.org, V-I-A-R-C-H. Don't go to that anymore. Somebody trolled it. It's a porn.
You should be able to tell the
So Moore's law is that telephone speeds only improve once every 100 years. I guess that's
On the previous slide, you were saying that memory is less than 5% of the total cost of the PC, but it's not completely linear. If we just ran into this where we ended up having to drop back to 500 megabyte chips because the gigabyte chips are just much more expensive, but much more than double, like 4 times as much.
Right.
So it's non-linear when you get up to the high end. When you go to the speeds of the processors, which are running around 2 gigabits, you ideally like to have 2 gigabytes of memory, but it becomes exorbitant, so we had to settle for half.
That's right.
So in that area, that move just doesn't apply.
I should qualify that. My rule of thumb is don't spend twice as much for twice as much performance. If you can get, if you can stay at the 1 gigahertz area and buy more machines, then,
That's what it is.
yeah, it turns out that not only do you get the implicit benefits from clustering and implicit load balancing, but stuff that's 1 generation behind is always a quarter, not half the cost of the other. So you can certainly buy more machines. Let me finish up. This is actually, we're developed a presentation that we never presented, and so this was back in '95 that we put this all together, so it wasn't all that bad. They only recently has the network, as the LAN really made its jump up to keep up with the slow, progressive, and Moore's law paced improvement of the other 7. But you know, when you go from 1 gigabit to, or when you go from 100 megabits per second to 1 gigabit per second, that's more than the lowest jump. So you could afford to wait for the $50 card. Now you still don't get, you definitely, with the Linux drivers now, you can get 12 megabytes per second out of the fast Ethernet card. You get 800 megabytes per second out of a gigabit card. But the latencies are still a problem for people with tightly coupled interdependent cluster nodes. Well, that's pretty much it. Oh yeah, so I have a couple links here. I've actually brought some of these websites up. This one is something of a commercial site. They make announcements of new packages, new upgrades, patches, things like that. Beowulf.org, like I say, it's something of a legacy site. There's nothing new on Beowulf.org. This one, Linux Cluster and Information Center, based out of Massachusetts, it's got a lot there. It's got analysis of system administration packages. It's got reviews of books. It's quite a nice site. This site, I'm going to give Jerry my presentation probably in the next 24 hours. I'll either have it on that site or at Blue will have a link to it from my website. And that's about it. So, kind of got it pretty well.
Okay, thank you very much.